Let us discuss about Sommerfeld quantum theory. Before going into detail of this theory, let us recap the Drude model of free electrons in metal. In the Drude theory or in Drude model, metals were considered consists of electrons as free electrons moving in a constant potential background. In the Drude theory, electrons were assumed as identical and distinguishable, and also classical theory or classical statistics, that is Maxwell-Boltzmann statistics, was applied. But there are few drawbacks of this approach. That is, we can say electrons cannot be treated classically as they are fermions. They are identical and indistinguishable, and they obey Pauli Exclusion Principle. And therefore, these observations imply that electrons obey Fermi-Dirac statistics. So, in Sommerfeld quantum theory, it retains almost all aspects of Drude model, but with few modifications. And these modifications are that electrons are treated with Fermi-Dirac statistics and recognizes that their energies are discrete. That means it treats them like a particle in a box of constant energy. And in this theory, it uses Pauli principle to distribute them in available energy states. So, with these modifications, Sommerfeld treated an electron as a quantum mechanical particle, which may be represented by wave function psi, and therefore this wave function can be used in the writing of Schrödinger wave equation. In Sommerfeld theory, it is considered that electron is lying in a one-dimensional box, we can say, with size as x is equal to 0 to x is equal to a, as we are considering it is along x-axis, one-dimensional box, such that electron cannot go out of these limits. And for that, it was considered that the ends, that is at x is equal to 0, the potential is infinite. That means electron is bound here, and x is equal to z is a is equal to, the potential is again infinite. So electron cannot go out of these limits of x is equal to 0 and x is equal to a. Considering these points, Schrödinger wave equation for the free electron may be written as plus 2me divided by h cross square into wave function psi equal to 0. And here important point is that we have considered v is equal to 0, because inside these limits the electron is free, and for free electron v is equal to 0. Here E is the kinetic energy of the electron, and we know that kinetic energy of electron E may be written as half mv square, which can also be written as p square over 2m. Now if we substitute this value here, this part, then we can write 2m over h cross square into this p square over 2m. It gives me 2m cancels, we get p square over h cross square, where p is momentum of the electron, and we can write this ratio as k square, and which is also called propagation constant. And using this propagation constant, this equation we can write again del 2 psi over del x square plus k square psi equal to 0. The general solution of this equation may be written as psi x is equal to, let us say, a times sine of kx plus b times cosine of kx. Means this equation, if we substitute the value of x here, then this equation will satisfy this Schrödinger wave equation. And therefore let us put the values. These are boundary conditions. We use boundary conditions, that is at x is equal to 0 and at x is equal to a, psi will be 0. That is, at psi is equal to, at x is equal to 0, psi 0 will become a sine of 0 plus b cos of 0, which implies psi 0 will be 0 at that. This is a sine 0 means 0, this is cos 0 1, they will be left with b, which shows b is equal to 0. And therefore the equation, that is solution, becomes psi x is equal to a sine of kx. Now at x is equal to a, this equation will be a sine of ka. So that gives the solution of the Schrödinger wave equation. And at this point sine a will be equal to 0. It means this portion will be 0 at psi at a, which implies that sine function will be 0 only if ka is multiple of pi. That means ka is equal to n pi, which gives me k is equal to n pi over a. Therefore the solution becomes psi x is equal to a sine of n pi over a into x. K, I substituted value of k. So this is the solution of Schrödinger wave equation, where n is a positive integer. That means you can take 1, 2, 3 and so on. because here n cannot be 0, which means that electron remains at rest at all the time. But since the particle is always in motion, as it is also considered in free gas of electrons in metal by Drude theory, therefore we consider that n will have some value greater than 0. Now here in this equation we do not know about the value of A, and this can be determined by applying the normalization of this function, that is total probability of finding the electron in the box, one-dimensional box, is 1, and that probability P may be written as the square of this wave function over all limit of the box, that is from 0 to A, and particle must exist in this box, that is equal to 1, and therefore this equation may be written in terms of function, that is we take integration from 0 to A of this function that is given by this. Therefore A sine of n by x divided by A square dx is equal to 1. Since here A is constant, so we can take A square common here, A square 0 to A integration of this function, that is sine square n by x divided by A dx equal to 1, and we know trigonometrical relation that sine square x may be written as 1 minus cos 2x divided by 2. So using this relation we can write equal, this will come out to be A square by 2 0 to A integration of 1 minus cos 2 n by x divided by A dx, and it should be equal to 1. Now since this is a cos 2a nx is a cyclic function, so it will be 0 from whole limit from 0 to A. Therefore we will left the integration of dx only, which gives me A square by 2 integration of dx from 0 to A equal to 1, and it implies that this is equal to A only. Therefore A square over 2 into A is equal to 1, and it implies that A will come out to be 2 divided by A square root. So that is the value of A. Let us substitute this value in the equation of solution. So we get solution psi x is equal to 2a into sine n by x over a. So this is the solution. That means now electron inside the one-dimensional box is given by this function. So quantum mechanically an electron is represented by this wave function. and the square of this wave function will give us the particle, the presence or the probability of finding that particle in a particular limit of that one-dimensional box. Now, after finding this wave function for that electron, free electron in the one-dimensional box, let us now find what is the energy acquired by this electron at different moments. For that, what we do is we can use these two equations. One equation is here, which we have written equal to this K. From here we know that energy is equal to P square by 2m, and we from here we have determined that K is equal to n by A. Let us have this equation as equation 1, and another equation we have here, that is 2m over h cross square, value of E is equal to K square. So from here we can write 2m E over h cross square is equal to K square. So let us match this equation and this equation and write down a new equation, that is, we will write here K is equal to 2m E over h cross square root, and we have K is equal to n pi over A. So let us now match this equation. On rewriting these equations, we can write n pi over A is equal to 2m E over h cross square root, which gives us E is equal to, from here I can find E by squaring this term, that is n square pi square over A square multiplied by h cross square over 2m. As we find in this equation, pi, a, h, 2m, all these are constants, but only n, that is positive integer, it varies. Therefore we can write that the energy of electron will vary only along with n, so we can write it as n square pi square over 2m a square into h cross square. So it varies only with this n. For example, for n is equal to 1, E1 will be equal to pi square h cross square over 2m a square, or you can say for n is equal to 2, E2 will be equal to 4 times pi square h cross square over 2m a square, and so on. So we can find for any number what is the energy of electron. So having the energy, electron will have discrete energy, and that energy if we show in the form of energy level diagram, so we can show that for n is equal to 1, this is the energy, and for n is equal to 2, that's second energy level, and for third, distance will increase as it is increasing with the square, so E3 will come somewhere here, and similarly fourth energy level E4 will come here, and so on. So this way energy level diagrams can be shown. For example, if E1 we keep E1, then E2 will be number 4 times E1, that energy will increase, and E3 will be 9 times E1, and similarly E4 will be 16 times E1. So the energy level, that means height of the energy level, will increase with the number, and therefore we can write that energy in the nth or level will be just directly proportional to n square. and this square term means it is a kind of parabola, and which can be shown like this. For one-dimensional box, this parabola may be shown as it will increase like this. So energy of electron will increase with the increase of n. That means if n will increase, then energy will also increase like along this parabola. Now, according to Sommerfeld model, the electrons inside the metal keep on moving inside the metal, occupying different energy states. But at 0 Kelvin temperature, the electrons occupy the lowest possible energy states. The Pauli Exclusion Principle restricts the electrons to go into an energy state. According to the principle, only two electrons can occupy any energy state, one with spin up and another with spin down. Only two electrons can be accommodated. Therefore, at absolute zero temperature, the electron occupy the energy state only up to a certain maximum energy level, which is called Fermi level, and the energy corresponding to this level is called Fermi energy. For example, at 0 Kelvin, if we want to fill up the electrons in these energy levels, then we know one electron will come in the first orbit with spin up and other will come with spin down. Similarly, in second also, one electron will come with spin up and other will be with spin down. That means we cannot fill more than two electrons in any of the orbit. Similarly here you can put here. So let us assume all these three energy levels are filled with two electrons, and last electron, let us say, that is filled here. So from this example we understand that E4 is the energy level below which all energy levels are completely filled, and above this level all energy levels will be empty. Therefore, this level will be considered as Fermi level, and energy corresponding to uh, this level will be considered as Fermi energy. That means Fermi of this level will be taken as Fermi energy. So if we mark this energy level with number NF, that means Fermi number, then we know the total number of electrons up to this Fermi level will be equal to number of electrons in each orbit, that is twice the number of levels. That means 2 into NF. So total number of electrons accommodated up to energy level will be equal to, we can say, N is equal to twice the number of Fermi level, NF. Now we can find what is the energy of this level, EF. That is equal to EF, we can find equal to NF square. What is Fermi number? That is square here. Then pi square we have. Then H cross square divided by, we can write 2ma square. So that is the energy of this Fermi level. And we know that NF is equal to n by 2. Therefore, we can also write it as n square pi square h cross square divided by 8 ma square, because this 2 will multiply by here. So 2 to the 4 and this 2, 8. So this is the expression for Fermi energy of electron inside the metal. So let us write Fermi energy as n square pi square h cross square divided by 8 ma square. So this is the Fermi energy of the electron system. Now if we want to find what is the total energy of the electrons, then we know that below Fermi energy there will be even number of particles, and if there are n number of particles or electrons in the system, then naturally there will be n by 2 levels. That means n will be equal to n by 2 levels. And if we add the energy of each particle, that means energy of one particle plus energy of second particle plus energy of third particle plus energy of fourth particle and so on. If we add the energy of all those particles, that will give me the total energy of all the particles. And to find the total energy, we can write, let us denote total energy is equal to E naught. That will be equal to twice of the number of particles arranged in n by 2 levels. That means level 1 to n by 2, and this energy I have to energy of each particle mean each level energy, and for that put the value of En from here, from this part we have used here. We will get n square h cross square, not n square I have to add. So let me keep constant terms outside. So let us write down pi square h cross square over twice of n and summation over n square from n is equal to 1 to n by 2. So I have to add all these numbers, and that will give me total energy of the system. But we know in the summation terms here, we know the standard result, like if we have summation over n square from, let us say, n is equal to 1 to some number s, it will be given by 1 square, let us say 2 square and 3 square plus so on, up to it will go s minus 1 square plus s square. So I will add all these numbers, square of all the numbers, and this is written as a result, standard result, that is 1 by 6 times 2s square plus 3s plus 1 into s. So that is the standard result we can use. Here instead of s we have here n by 2. Therefore let us use this result in our equation here, and we find total energy E naught, E0 will come out to be, let us say, okay, before writing this, let me just simplify it. It further comes out to be 1 by 6 times s into, inside we will write 2s square, because this n square, 2s square will be quite large as compared to this 3s plus s as I multiply inside. Therefore we get only 1 by 6 s into 2s square. By using this result, we can write now our equation of energy E naught is equal to 1 divided by 6, 1 divided by 6 n by 2 that is the value of S here, into twice n by 2 whole square into, now remaining terms I have written the value of this, now pi square h cross square over 2m, that will go along with. Now on solving it, we can write 1 by 2 n times n square pi square h cross square over 8 m a square. Now in this equation we know that this part is nothing but it is equal to Fermi energy here, n square pi square h square this. Therefore I can write it equal to 1 by 3 n times Fermi energy. So it shows that total energy of electrons up to Fermi level will be equal to 1 by 3 n e f. And if we divide this energy by n, that will give us the average energy of electrons. Therefore, let us find average energy, that is, let us denote it by bar, will be equal to E naught divided by capital N. So I take this n number of electrons to left hand side, I left with 1 by 3 EF. So it means that the average energy of all the electrons will be just 1/3 of the Fermi energy of all the system. That means if we have assumed that Fermi energy is the energy of this level, then average energy of all the electrons below this level will be just 1/3 of the energy of electrons in this level. So that is very important kind of result. And at this level you can find what is the velocity of electron inside the metal when it is having energy equal to Fermi energy. And the velocity of electron at Fermi level is called Fermi velocity, and that can be determined if we put the energy equal to, that is kinetic energy due to this Fermi velocity will be half mv square is equal to Fermi energy, which we denote here in this case. Therefore let us write n square pi square h cross square divided by 8 m a square. So this is our Fermi energy, which is in the form of kinetic energy, and this is equal to, from here this Fermi velocity may be written as equal to n square pi square h cross square divided by, taking this term to the other side, we left with 4 m a square whole square root, which will be equal to, all these terms are square terms. Therefore we can write equal to n pi h cross over 2 m a. And in terms of Planck's constant, not in h cross, we can write this Fermi velocity will be equal to n h, because we have to put 2 pi in the denominator, so we'll get 4 m into a. So this is Fermi velocity we get. That means the velocity of electron at Fermi level. Now we also know that the expression for energy of electron, uh, or let us say E only, is equal to, initially we have got n square pi square cross square over 2m. Now this energy depends upon this number of shell. Therefore, let us try to find how the energy changes with the number. Therefore, differentiating both sides, this equation we get dE is equal to, let us say, pi square cross square over 2m multiplied by this 2n dn. This thing we get from by differentiating this equation. And from here, if I write it this equation as dn, let me take this de to this side, I get de is equal to, all these terms go to other side, 2 cancels, so we get m a square divided by pi square cross square multiplied by 1 over n. So this is, and this is nothing but it is the number of energy states in a particular energy limit. That means it gives, this equation gives me the number of energy levels per unit energy range of dE. So we can find in a particular range of energy how many energy states will be there for an electron. So this energy range we can find dE, and this, in this, dn number of energy levels will be there or states will be there. Now we also know that there are two quantum states possible for each energy level. That means one state upward, another state downward, and therefore total number of energy states per unit energy range may be given by twice of the number of energy states in given energy range, and this thing we will write as energy density. That is, we can say density of states. Density of state will be written as ZE, that means in the range of E, that is equal to this. And if we write down this expression here, then we'll get 2m a square over pi square cross square into 1 over n. So from here, from this expression, we can also find what is energy states in terms of energy, because we know that energy is equal to n square pi square cross square over 2m a square. And from here I can find what is 1 over n, and that 1 over n will come out to be pi cross square divided by a times 2me square root. So if I substitute this value here, then we get ZE is equal to it gives me pi cross over 2me square root multiply by a into times 2ma square over this pi square and cross square. And solving it, because we have square root here, we have square root here of me, therefore this term comes out to be a divided by pi cross times 2m over e. So this expression, that means density of states, is nothing but it is inversely proportional to the energy. So the variation of density of electronic energy states with the energy may be shown in the form of graph, and it will come out to be like it will be like this curve, and naturally this side we are plotting energy. With energy it is varying, and density of states will come out to be this side, and from a certain energy, that is we can say Fermi energy here, Fermi energy, we will find that energy states will come out, density will be like this. That means as you increase the energy towards Fermi energy, the density of states will decrease gradually with this curve. And that is the outcome of this theory given by Sommerfeld, in which electrons are considered as fermions, and Pauli's exclusion principle is applied, and with that we came to know what is total Fermi energy of the system and what is average energy of the system. We have also derived expression for the Fermi velocity. In the end, we have determined energy states of the system. That's all. Thank you very much for watching this video.